Hey there, welcome. This is actually your last video lesson for Unit 4 on area of triangle sectors and segments. So this is the last objective, to be able to find the area of these things. And so maybe, just maybe, and it's a while ago, maybe do you remember this? From geometry? It's okay if you don't. You do this in geometry as well. We look at it a little bit differently because actually when you learned this in geometry, you didn't know about radians yet, right? And so we've hopefully seen some of the value of radians. So that can help us a little bit with this. So we know what a triangle is, and you might be staring at this being like, well, yeah, finding the area of a triangle is 1/2 base times height, right? And if you remember the base and the height, what has to be the relationship between that? They are perpendicular, right? Meaning they form a 90-degree angle. So this was true. This 1/2 base times height, or maybe you said base times height divided by 2, is true if you have, that rhymed, a right triangle. But as we've seen recently, we're talking about more than just right triangles, right? We're really extending on our understanding of this. So this is going to be to find the area of a triangle with any type of triangle, not just a right triangle. Like we don't need to, and I guess this wasn't necessarily just a right triangle, but like if we had a non-right triangle, we had the height. And so we're going to talk about some other ways of finding the area of a triangle, which I guess, yes, you could just find the height as well. We've been talking about that, but kind of other routes to find the answer as well. We're going to talk about sectors and segments. Maybe you remember these. A sector is like a part of a circle. So if I have this circle, a sector, like this right here is a sector. It's like a slice of the circle. That's a sector. If we're talking about a segment, we are talking about actually this part. So I cut that and it's like the sliver. It's like the crust. Made myself laugh. So yeah, and so maybe you remember that. So like maybe you're saying this, you're like, oh, okay, I know how to do that. You can see how this all ties in together. Oh, well, if you're finding a segment, it's the sector and you have a triangle, right? So your homework, and this is just the one assignment that goes with this, is the textbook. So practice with this after, and you'll see how some of the things that we've learned about triangle trig, whether it's right triangle or non-right triangle, is going to come up in this. So area of any triangle. When two sides and an included angle are known, we've got this formula right here, 1/2 AB sine C. Okay, so C is the included angle, right? So I've got this triangle. I know A and B, and I know angle C, right? This is actually the same formula that you guys use with a right triangle. But the included angle would be 90 degrees, right? So if I knew A and B, and I was going to find this, I would have 1/2, if I use this formula, AB sine of 90. But oh my goodness, what's the sine of 90? We know that. And we know that's speedy. 1/2 AB times 1, so it's just 1/2 AB, right? So this is actually the same formula that you've been working with. When all three sides are known, we have something called Heron's formula, right? So it's the area of S, which we'll talk about what that means down here, times S minus A, times S minus B, times S minus C, where 1/2 A plus B plus C, right? Those are the sides of the triangle, is the semi-perimeter of the triangle. So this is when you know all three sides. This is if you know two sides and an included angle. We do have ways, if we know three sides, to find an angle, right? We've just spent time working with the law of sines and the law of cosines. Right, so you do have methods or ways that you're not tied to using just one of these formulas unless you're told to use Heron's formula. right? That would be something. But if you had all three sides and you felt more comfortable using this formula, or this was the one that was prevalent for you, and we didn't tell you which one to use, or you weren't told which one to use, you can go ahead and figure out the included angle, store it in your calculator, and use this formula as well, right? So there's other ways that we can go about doing this. So let's take a moment and try these two examples. If you want to pause the video and try them on your own, that's not a terrible idea. So in example A, in this first one, we have two sides and the included angle, right? So I'm going to go ahead and it's A equals 1/2 12 times 5 times the sine of 120, right? And I can show my setup, and I'm apologizing, I'm on the computer where I have a calculator attached to it. So you're just going to make sure that you're in the right mode, right? So I've got to be in degree mode for this. So I've got 12 times 5 divided by 2. So I've got A equals, isn't that a special angle? 30 times the sine of 120. Don't we know what the sine of 120 is? Wouldn't that reference angle be what? 60? And that would be in quadrant 2. Well, we know this. We don't need a calculator. What am I talking about? Right? The reference angle would be 60, and it's in quadrant 2. The sine of 160 is √3/2. It's in quadrant 2, so it's positive. So, oh my gosh, we actually know this without a calculator. How fun is that? So I actually get 15√3. It's area, so units squared. I don't know the units. All right, let's see. 30 sine of 120. If I just plugged into my calculator, I get approximately 25.981 units squared. Oh my gosh, I put it in wrong. Which, oh my gosh, that's what this is too. So we actually didn't need a calculator for this. How cool. You're really bringing in some background knowledge here. Special angles. Know your unit circle. Yay. Okay. So in this second one, right, so like this one was an example of side, angle, side. This one is an example of side, side, side. Right? I've got all three sides. So the more appropriate formula, if I wanted to get my direct answer, is let's use Heron's formula, which hopefully you wrote down from the last slide. Right, so I want to find the semi-perimeter. So 1/2 of 7, oh wow, no, plus 13 plus 9. 7 plus 13 plus 9 is 20. Oh no, it's not, 29. 29, half of 29 is, oh my goodness, 14.5. All right, yeah, 14.5. So that's the semi-perimeter. So then we've got area is going to be the square root of the semi-perimeter times the semi-perimeter minus 7 times the semi-perimeter minus 9 times the semi-perimeter minus 13. Right, so the area is going to be the square root of 14.5 times 7.5 times, what's 14.5 minus 9? 5.5? Oh no, it's not 0.9, it's 0.5. 14.5 minus 13 is 1.5, right? So that's going to give me, let's see, 14.5 times 7.5 times 5.5 times 1.5, the square root of this nice number. My computer is having some struggles today. And then the square root of that We get 29.953. Area units squared. Right, so that's using Heron's formula. If you wanted to find one of the angles, you could do that, right? Like I could go ahead and find angle R and then use this formula, right? If I wanted to go ahead and, nope, I couldn't find the height here, could I? No. I don't believe I could. I don't have an angle. I don't have enough. Here I could have found the height, right? Like I could have been like, I'm going to find this height, right? No matter where it is, I believe I could have, right? I could use this angle, which I know is its supplement, and said it was 60 degrees, and then said the sine of 60, 12 times the sine of 60, right? Which the sine of 60 we talked about, it's root 3 over 2. So I would have 6 root 3 would be the height. And then you could do base times height divided by 2. And I could do 6 root 5 times 5 divided by 2. And oh my gosh, that's a 3, sorry. Oh my gosh, I get what? 15 root 3, right? So I could do that, but think about like what this gives me as well. I could use the law of cosines and say 13 squared equals 7 squared plus 9 squared minus 2 times 7 times 9. My computer has a major delay right now. Times the cosine of r, right? And then I'm going to, if I isolate the cosine of r, I'm going to get the cosine inverse of 13 squared minus 7 squared minus 9 squared all over negative 2 times 7 times 9 is going to equal to r. And then I could go ahead and use this formula. That's just a little more tedious, right? And we do want to be aware of how to use this formula as well. Okay, let's keep going. So what about this one? So find the area of a regular pentagon inscribed in a circle with a radius of 3. So if something's regular, that means that it has all sides are equal and all angles, I guess interior angles and exterior. It's probably poor wording. That's okay. So, right, so the radius of the circle is 3. Pentagons have 5 sides, if that wasn't drawn for you. 3 inches and 3 inches. Right, so all of these sides are congruent. They're not all necessarily 3. They're probably not all 3, actually. Right, but we do have this isosceles triangle right here. Good geometry term. So we know that like these angles are congruent. We know that if I were to draw these other ones in, these interior, like these angles in here are equal, and I'm going to have 5 of them, right? So I could actually find this angle right here, this one, by doing 360 divided by 5. So it's 72 degrees if you didn't know that. So I've got, this is an example of side angle side. Right, so I've got my formula, area equals 1/2 AB times the sine of the included angle. So the area is going to be 1/2. Well, it's 3 times 3, so I'll go with 3 squared times the sine of 72, not a special angle. So the area is going to be 4.5 times the sine of 72. I'll go with A1 because it's just one of them. Right, and so I have 4.5 times the sine of 72. And I get that one of these triangles is about 4.27, 1.28. Is it inches? Inches squared, right? And then I just need to remember, well, I'm finding the area of the entire pentagon. So I want to take that 4.28, whether I store it in my calculator or it's literally still in my calculator, and I want to multiply it by 5 to figure out that entire area, right? So that's going to give me, I should have done that, sorry, times 5, 21.399 inches squared. Kind of extending on that, right? Or maybe I would have done 4.5 times the sine of 72 and taken that and multiplied it by 5. And then 4.5 times 5 gives you 22.5. If I wanted to do that way first as well. All right, so some extending on a little bit. So let's now talk about the area of a sector. And so as I said at the beginning, a sector is like a slice, right? So I have, this is a sector. It's a slice or a piece of the circle. So this right here is theta. This is the radius. We know that these are both the radii. So to figure out the area, remember this is if theta is in radians, you have 1/2 r squared times theta. Well, why does that work? Well, how do you find the area of a circle? Right, to find the area of a circle, you maybe remember that it's pi r squared. If I'm going to find, and let's pretend we're not dealing with radians yet, let's say we're working with degrees, right? If I want to know what fraction of the circle, actually, no. Let's deal with it in radians, right? So like this is how much you want to figure out the fraction of the circle. Well, that's going to be theta over 2 pi, right? Like it's an entire circle is 2 pi. So it's just like, you might remember doing this with like x over 360. Right, and you find the degrees, like what portion of the circle are we working with? Like, am I working with 1/4 of it? Well, that's 90 degrees over 360. Or that's pi over 2 pi. So I want to figure out like theta over 2 pi. So if I took this, I'm going to really be multiplying the fraction of the circle that we're dealing with times the entire circle. So you have theta over 2 pi times pi r squared. Well, if we simplify this, I've got theta over 2 times r squared. Well, I can rearrange this a little bit, and that's what this formula is, right? I've got 1/2 r squared times theta, and theta is in radians, right? So if you're given it in degrees, you can convert. Not as useful, but it's the same idea as doing this, right? You just have a more bulky formula going on. For a segment, now let's combine these two ideas we just talked about, right? So this is theta. Like, think this is a circle. Oh, goodness. Oh, goodness. That wasn't the worst thing I've ever drawn. This is the center of the circle. Okay, maybe it wasn't great. I'm working on it. I'm not great at it yet. So these are both R. Well, I can now really combine these two ideas of area and sector area. I'm sorry, area of a triangle and sector area. And I can figure out, well, what is the area of the sector minus the area of the triangle? Is going to equal to the area of the segment, of the crust, of this part. Right? So, oh goodness, sector minus triangle. So I've got the sector minus the triangle. Right? That's what we worked with. This is the area of the sector. This is the area of the triangle. Because this is the radius, you're going to have these two sides, and you have this interior angle. If it was given to you like this, and let's say we didn't know this theta, and I knew that this was 40 degrees, you would know that this was also 40 because they are isosceles. Like these sides have to be equal. It is a circle that we're dealing with because we're dealing with a sector, right? So these two are both 40. And then, oh, this would have to be very not drawn to scale, but 100, right? And then I could work with this and I could say, well, I'm going to convert 100 degrees to radians, right? 100 degrees is going to be pi over 18 radians, right? And I could go ahead and say, well, I have 1/2 times, let's say the radius was 4. So 4 squared, so 16 times pi over 18. That's going to be the area of the sector. And then because I want the area of the segment, then I would do 1/2 base times height. I mean, I have 4 squared, right? Times the sine of pi over 18 or whatever I wanted to work with there, right? Not a special angle the way I just did that, right? And so this works because if you're dealing with a quarter of a circle, you're taking the area of the circle and dividing it by 4, which is 90 degrees, right? And then when you do this, it's just the same area that you've always worked with. Pretty cool, right? Oh, goodness. We can, I don't know how to clear this out. We can simplify this a little bit if you would like, right? So here, what's happened because this, as I said, is just r squared. I'll rewrite it over here. You can factor out that 1/2 and r squared, and you'd be left with theta minus sine of theta if you want to simplify it and work with a slightly more simplified formula. And just remember that both of these, we're dealing with theta in terms of radians. That's what the theta is representing for us. Like if I have an angle measurement, I can't just stick it in right here. I'm sorry, if I have a degree measurement, I can't just stick it right here. It doesn't work the same way because radians, it's like 1 radian is 1 radius length around the circle, and that's not the case for degrees, right? Okay, so in this video, we accomplished our last objective of this unit, and we looked at finding area of triangles, sectors, and circular segments, right? So go ahead and work on this. We will do another example when we see you. We only see you for a little bit, but we will do another example to answer questions and make sure that we're clear on this and see what else we're not clear with. But this is the last objective of Unit 4. Congrats, exciting. And make sure that you get some practice in and you're ready to ask some questions before class. See you guys next time.